Okay, so I'm recording this video so that we can try to get caught up with where we're supposed to be uh, in general chemistry at this point. From missing a lecture last week and just from being a little bit behind due to issues with the projector, we just had a little bit of catching up to do. So uh, this will cover most of chapter five, and then we'll jump in the next lecture into chapter six. A lot of which we've actually already done. A lot of that was the things like the naming of the ionic compounds is in chapter six, and we've already covered that. So we won't cover it again in class. You'll just be responsible for that material from now on. So chapter five is quantum theory and the atomic structure. So this is picking up where we left off, talking about the Bohr model for the hydrogen atom. And importantly, the Bohr model is very good at describing hydrogen, but it's very bad at describing anything except hydrogen. In fact, it just doesn't work for anything besides hydrogen. And the principal reason why the Bohr model fails is because it sort of only goes part of the way there. It tries to behave in a classical fashion, but with everything except the energy orbits themselves. So let me explain that a little bit better. So in the Bohr model, we had something like the proton here, and then we remember we had these orbits, n equals 1, and here's another orbit, n equals 2, and so forth and so on. And so, what was different about the Bohr model was because these orbits were restricted to locations where the wavelengths were whole number integer values of going around the orbit here. It was in some sense quantized because the electron had to be here or the electron had to be here, and it could transition from one place to another place, but it could not be somewhere in the middle. Like the electron just could not be here. That was not allowed. But other than that, it treats the electron exactly the same way that you would treat any kind of particle. It was still a particle. It was still moving around, sort of in an orbit. It was just sort of trapped on these orbits, and it could jump back and forth between them, but it couldn't orbit someplace in the middle, so to speak. So it's kind of like trying to have your cake and eat it too. It surrenders some of the weirdness of quantum mechanics with these wavelengths ideas, but it doesn't go all the way and accept a wave particle duality of the electron. And so this is really shown by the Heisenberg uncertainty principle. You don't need to know what the Heisenberg uncertainty principle is, other than basically what it says is that we cannot know both the position and the momentum of any particular particle to 100% precision. So this delta x means the uncertainty in the position. This delta p means the uncertainty in the momentum. If you don't know what momentum is just mass times velocity. So you take the mass of the electron and multiply it by its speed, and that tells you its momentum. So really, this is sort of where the particle is and how it's moving. You can't know both with specificity. You can't know exactly where the particle is, and you can't know exactly how it's moving. In fact, you have to have a little bit of uncertainty in each of those things, and the product of the uncertainty has to be greater than or equal to h over 4 pi. Again, I'm not going to explain where this equation comes from. You would have to take a bunch of physics classes to be able to understand this. But what is interesting is that this h remembers the Planck constant, and it's a very tiny number, 6.63 times 10 to the minus 34 joules times second. So this number is incredibly tiny. So the uncertainty here can be quite small, and really it only shows up when we're working with small objects like an electron, where you're really trying to precisely define exactly where the electron is. Whereas if you're working with a baseball, there's the uncertainty here is so small that you won't ever really notice it or observe it in sort of everyday sized objects. So whereas in using calculating the trajectory of a golf ball or a baseball, you can certainly use standard classical physics, and the Heisenberg uncertainty principle is not going to be a problem. When calculating the way the electron moves around a nucleus, the Heisenberg uncertainty principle is a problem, and it's manifested in all atoms except for hydrogen. So you can get away without thinking about this for hydrogen, but you can't get away with it with any other kind of atom. So how do we go about fixing this? The way that we go about fixing this, if I can get this to work, let me see what's going on here. Yeah, there we go. Sorry. Um, this is a different program I'm using, and I'm not used to the way some of this stuff works. So what we have here is the idea of something called the Schrödinger equation. So Schrödinger, in I believe it was 1926. There it is. In 1926, Schrödinger introduced wave mechanics, and he did so by proposing that Newton's equation F equals ma essentially gets replaced by this equation that he was proposing. This is called the Schrödinger equation. You do not need to know this. This is not something that you're going to need to recreate. It certainly isn't something you're going to solve. This is way beyond the mathematics of a general chemistry course. But I just want to show it to you because I feel that everyone should at least see the Schrödinger equation at least one time in their lives. And really, I'm going to fix this because it annoys me. There we go. The Schrödinger equation. Let's see what it tells us. So first of all, there's a couple of important things in here. We see the Planck constant is in here. We see pi shows up as usual. Pi shows up in weird places. We see this value m. That's the mass of an electron or the mass of a particle that we're talking about when using the Schrödinger equation. This symbol is called a del symbol. And it's a mathematical symbol. It's not something that you need to worry about. So this symbol psi is something that you need to worry about. It's called the wave function. So what the Schrödinger equation says is that if you take a wave function and apply this mathematical operator called the del operator using the Planck constant as well as V, which stands for potential energy, you apply these things to this psi, and what you get out is the total energy of whatever this psi is. So this equation is actually used to find this thing called a wave function. So the wave function isn't something that you sort of find elsewhere. You use the Schrödinger equation and some higher level mathematics to figure out what the wave function is. In practice, we use computers to do this. So solving the Schrödinger equation explicitly for systems is often impossible, and instead we use computers to solve this equation at least approximately and to give us wave functions. And we'll see wave functions a lot for the rest of this chapter and for the rest of this year. So the state of the system is given by a wave function. So you can think of the wave function as replacing the orbits that we saw before. So in the Bohr model, we had n equals 1, n equals 2, n equals 3. Each of those were orbits. We're replacing those with wave functions. So what are the wave functions? First of all, what are they functions of? They're functions of spatial position. So what you would do is, as an example, you would take your nucleus, which I'm going to call a proton here, and you might call that spot 0. And then you would have a z-axis, you would have an x-axis, and you would have a y-axis. And you might find a point here in space that you could characterize with an x, a y, and a z. That's supposed to be an x, sorry. An x, a y, and a z. And that's what you plug into. You find this spot and you plug it into this wave function. And so then what does the wave function tell you? Well, it tells you what's called the probability amplitude, which is a weird thing. This wave function is actually a complex number, so it has imaginary numbers in it, square roots of -1 and all kinds of weird stuff. So the wave function itself doesn't tell you a whole lot of much, but the square of the wave function, you plug in the numbers and then you square the answer you get. And the answer that you get, well, first of all, it's a squared number, so it's always positive. This number can be negative. It can also be complex. It can have square roots of -1 in it. But when you square it, you get rid of all that stuff, and the only thing you get is a positive number. And that positive number is the probability of finding the electron at that spot. So how probable is it that you find an electron at this point? Technically, it's a probability density. You have to multiply it by a little box of volume around this point because your likelihood of finding the electron at any one exact point is 0. But you might look at a little region of space around this point and say, what's the probability of finding the electron somewhere in this little box? And that's what the wave function tells you. And so what you can do then is you can take a computer and you can plug in all of the possible X, Y, and Z positions. So you might find a spot over here that's X, Y, and Z. There's a point there. There's a point up here. There's a point up here. There's a point over here. There's a point down here. There's a point on here. And you tell the computer to graph the probabilities of finding the electrons at all of those places. And what it will typically do is it will graph darker the regions where you're more likely to find the electron, and it'll graph less darkly the regions where you're less likely to find an electron. And you'll find lots of pictures like this in your textbook. And what we do is we take those pictures and we simplify them, and we say, okay, we're going to draw a picture of what we're going to call an atomic orbital. So an example of an atomic orbital, this one we're going to see is called an s orbital, is just a sphere. And so the nucleus is down here inside of this, and we say that there is some probability of finding the electron inside of this spherical region, and that is the orbital of the electron. Now, why do we say probability? Because remember, the Heisenberg uncertainty principle says we can't know for certain where the electron is, and we can't know for certain how it's moving. But we can know some statistics on where it is, some probabilities on where it is. And so this wave function follows, or excuse me, this Schrödinger equation follows the Heisenberg uncertainty principle, because it doesn't tell you exactly where the electron is. It doesn't tell you the exact way the electron's moving, but it does tell you the probabilities of finding the electron in some region around the nucleus. And the picture of that probability distribution is called an atomic orbital. So each orbital is going to be labeled with a set of quantum numbers. So just like in the Bohr model, we had our proton, and then we had our n, which was a quantum number. It labeled which orbit we were talking about. So we had n1, and then we had n equals 2, and then we had n equals 3. And that told us which of these orbits we're in. Which of these atomic orbitals we're in is also going to require a quantum number. But in this case, it actually requires 3. You have to have 3 to tell which orbital you're in. You need the principal quantum number n, you need the azimuthal quantum number L, and you need the magnetic quantum number, ImSub. So each of these wave functions in a hydrogen atom, or in any atom, we would say, here's psi. We're going to label it with a set of numbers. We're going to have an N here, we're going to have an L here, and we're going to have an ImSub. So example, you might see something like psi 210. That would be one solution to the Schrödinger equation. By the way, I don't think I stated this explicitly. The Schrödinger equation will typically have infinite numbers of solutions for any different particular system. So when you say we solve the Schrödinger equation for the hydrogen atom, it's not just finding one energy state of the hydrogen atom, it's finding an infinite number of energy states. Now, they may have different energies, and we're going to see that they do have different energies, but just like we had an infinite number of orbits here, we could go 1, 2, 3, 4, 5, 6, 7, all the way up to infinity. We're going to have an infinite number of psis. And we're going to label those psis with these numbers. So this would be one wave function. A different wave function would be 1, 0, 0, and a different wave function might be something like 3, 2, and -1. Those are all examples of wave functions that we could encounter, and we're going to see that we need to be able to determine, if we see this wave function, what is the picture for that wave function? What is that atomic orbital is represented or representing that particular wave function? So what we're going to do is we're going to go through each one of these quantum numbers, and we'll talk about what their values are and what they're allowed to be, and then what that tells us about the shapes of the orbitals. Okay, so let's do that. Let's jump forward a little bit. So let's look at these quantum numbers. So the first quantum number is called the principal quantum number. It's given the value n, and this basically plays the exact same role as it did for the Bohr model in the hydrogen atom. It essentially tells you how far the electron is going to be from the nucleus. So again, we would imagine that there's some radial distance here, and the smaller n is, the smaller this radial distance is. Now, again, we don't know exactly where the electron is. We can't know exactly where the electron is. It's not allowed for us to know exactly where the electron is, Nevertheless, we do know the probability density, and what for small n, the likelihood of finding the electron closer to the nucleus is greatly enhanced. When you go to bigger n's, the likelihood, the probability of finding the electron somewhere close to the nucleus is actually smaller. So the probability of finding it further away from the nucleus is larger. So as n gets bigger, the size of our orbitals gets bigger. Additionally, as n gets bigger, the energy of the orbital gets bigger. So the farther away the electron is likely to be from the nucleus, the greater the energy is here, right? Because it's like pulling a bowling ball away from the center of the Earth. The farther away the bowling ball is from the center of the Earth, the more potential gravitational energy it has. Here we're pulling an electron away from a positive charge, and so that is increasing the energy of the system. So orbitals with larger n values tend to have larger energies. What are the values that n is allowed to be? They're allowed to be exactly like in the Bohr model: 1, 2, 3, 4, 5, 6, 7, 8, all the way up to as far as we want to go. So remember, with quantum numbers, you pick. So just like in the Bohr model, we said, okay, here is our first orbit, that's n equals 1, and somewhere out here is our 10th orbit, and that's n equals 10. And you get to choose which one of these you want to study. So you imagine, is the electron in the first orbit? Is it in the 10th orbit? And then we imagine transitions from the first orbit to the 10th orbit, or from the 7th orbit to the 10th orbit, or something like that. But you didn't have to have it as one of these. You got to pick and play around and see what the energy levels were for having it as any combination of n that you wanted. It's going to be the same thing here. Here, what we're going to find is that n is allowed to be anything that we want as well. We get to choose. As long as n falls within the rule here, you can't choose 0, you can't choose 2.5, and you can't choose pi. The only numbers you're allowed are the integers, 1, 2, 3, all the way up, the positive integers, in fact, so the natural numbers. Those are the only numbers that you're allowed to use for the value of n. Okay, so n's pretty easy. Sorry. Let me clear that off and go to our next slide here. So n's fairly easy. This thing is being a pain. There we go. The azimuthal quantum number L. So what is this azimuthal quantum number L? It determines the shape of the orbital, and along with n gives the energy of the orbital. So we're going to see that for most atoms, n and L together tell you what the energy of the orbital is. That's not true for hydrogen. For hydrogen, n is all you need. You don't need L to know what the energy of the orbital is. So we'll see a picture of this and how the hydrogen atom looks different from the other atoms. And when we see that, that picture will explain why the Bohr model works for the hydrogen atom and it doesn't work for the other atoms. What are the allowed values of L? Now, this one's a little tricky. Notice that the allowed values of L here are 0 up to n minus 1. What does that tell you? It tells you to know which are the allowed values of L, you have to pick an n first. So, for instance, we could pick an n, and I could say n equals 3. And then I could ask the question, what can I choose for L? And so the allowed values of L here will be, well, we start with 0, 0, 1, 2, but 2 is n minus 1. N is 3, 3 minus 1 is 2. So this is as far as I can go if n equals 3. So if you tell me I want you to look at n equals 3, then I will tell you, well, the only L's that I can work with are 0, 1, and 2. Okay? What about if n equals 1? Well, for that, the only allowed value of L is 0. What if n equals 4? Then I could have L be either 0, 1, 2, or 3. And it can be any one of these. These rules don't tell you what they are. They tell you what they can be. So the first rule says n can be any natural number, 1 through infinity. And L can be any natural number 0 up to whatever your n is minus 1. So that's choices you can make. Okay, and then what does the L tell you? It tells you a couple things. It tells you the energy of the orbital, but it also tells you the shape. So if you know that L equals 0, if you choose L to be 0, what is the shape of that orbital? That shape is this spherical shape. So the S doesn't actually stand for spherical, but we can pretend that it stands for spherical. Um, and uh, and it actually stands for sharp, and it comes from spectroscopy, so that's not something you need to worry about. But an s orbital is spherical in shape. So here we have three different s orbitals. This, when we see this designation, and we'll go over this again in a little bit, but the number in front, that corresponds to the value of n, and the number afterward corresponds to the value of L. So if we were to ask what psi, what wave function corresponds to this one s orbital, it would be the 1, 0, and then there's another number here that we would have to put. We're going to see that that number is 0. So this one would be the 1, 0, 0. This one would be psi. Here, n is 2. So this would actually be 2, 0, 0. And this psi would actually be 3, 0, 0. And again, we'll learn what this third number is in just a few minutes. So the second number here, that corresponds to L, and that tells you the shape. If that number is 0, then we're talking about a spherical shaped orbital. Also note that as we go from n equals 1 to n equals 2 to n equals 3, this orbital gets larger. So again, we said that n tells us the size of the orbital. You can see that the 1s orbital is smaller than the 2s orbital, and the 2s orbital is smaller than the 3s orbital. And finally, s, all the values here for the L's are the same. This is L equals 0, this is L equals 0, this is L equals 0. All s orbitals have L equals 0. Every single one of them. That's a one-to-one correspondence. That's definition. If it's L equals 0, we call it an s orbital. So the energies here, we can rank these, that this is the lowest in energy, this one is the next highest, and this one is the next highest. Why? Because n's getting bigger. So L and n tell you the total energy. Here we have the same L's, and so the n gets bigger. That tells you that this 1s orbital is lowest in energy, and this 3s orbital is highest in energy. Okay, what about p orbitals? P orbitals look like little dumbbells. So you'll often see me draw these kind of like this. Sometimes I'll draw them sideways. Sometimes I'll draw them kind of coming in and out like this. But nevertheless, they always look like this sort of p orbital dumbbell shape. Okay, so that would be when L equals 1. So this, what would this one be? This one would be some psi. It would have some n associated. We'll see which ones we can have here. But then the next number here would be 1. That's supposed to be a 1, not an L. The next number would be 1, and then we would have an m sub L. So as an example, we could have psi 2, 1, 0. That would be an example that would be an orbital shaped like this. Sorry, I keep hitting the wrong button there. Next, we have L equals 2, which are the d orbitals. And those look like clover leaves, or they look like two p orbitals sort of crossing each other. It should be really careful. These are called lobes of the orbitals, and they're not. This is not 4 different orbitals. This is one orbital, and the orbital tells you the likely location of the electrons. So what this is saying is that if there's an electron in this orbital, then this is the highest probability of places of finding it. And notice there's sort of these, and same thing in this P region here. We have this region in sort of the plane, the XY plane, where there's no probability of finding the electron. That region is called a node. So we'll talk about nodes a little bit more, but that is the region where there's zero probability of finding an electron. And that would be in this sort of plane here for this one. Notice there are actually 2 nodes here. There's a plane that runs this way, and then there's a plane that runs this way. So there are 2 nodes in this one. Good. So that is this idea of nodes. So what we would say is that psi squared equals 0 for a node. Remember, psi squared tells you the probability of finding an electron, so psi squared equals 0 at a node. Okay. Now, these d orbitals, let's erase this so we can see them a little bit better. The d orbitals, again, they come in 2 different shapes. Most of them are going to have this cloverleaf shape. Some of them look like a p orbital with a donut around it. So this is a bit of a weird, a weird orbital structure. But it is what it is. That's called the DZ squared orbital. By the way, I want you to know and be able to draw and recognize the shapes of these orbitals, but you don't have to know their names. So you don't need to know, we're going to see these p orbitals are called px, py, and pz, and then we're going to see all kinds of names for the d orbitals, but you don't need to know this is dxz, and you don't need to know this is dz squared. You do need to know that this is a shape for a d orbital and that this is a shape for a d orbital. You just don't need to know their names. Now, we can keep going to higher values of L. Remember, let's say that we had n equal to 100. Well, then we could have L equal to 0, 1, 2, 3, all the way up to 99. So for n equals 100, there are 99 possible L values. We're only learning the shapes for the first three. So this one, 0, that would be an s orbital. The one there would be a p orbital. The 2 here would be a d orbital. The 3 is an f orbital, but you don't need to know the shape of it. And then after that, you just go in alphabetical order, G, H. No one ever actually goes above G. Really, you never go above F for the periodic table, but sometimes computational chemists will use things called G orbitals occasionally to study molecules. But no one really goes much above G or H, so you don't ever worry about all of these. These are too high in energy. Very similar to the hydrogen atom, the Bohr model for the hydrogen atom. Technically, n runs from 1 all the way to infinity, but you really only have to go out 10 to 15 energy levels, and you're already basically as far away from the nucleus as you can get before the electron just separates from the nucleus entirely and goes somewhere else. So although these are technically solutions to the Schrödinger equation, they're not solutions that matter. They're not ones that anyone uses. Excuse me. All right, so let's continue on then. So we've got two of our quantum numbers. The last one is the quantum number m sub L. This is called the magnetic quantum number. It determines the spatial orientation of the orbital, basically the direction the orbital points. So you can imagine if I have a p orbital, I can imagine it pointing up and down, or I could imagine it pointing left and right, and that would still be two different p orbitals. And what this tells you is that these would have two different m sub L values. The m sub L value will tell you, is it pointed up and down, or is it pointed left and right? So that's the basics about m sub L. It also tells you the total number of degenerate orbitals which exist in a subshell. So a subshell is just a particular set that has an n and a particular set of L, a particular value for L. So, for instance, we would say if we have n equals to 2 and L equals to 1, all of the orbitals that have those two numbers we would call a subshell. We would call that the two, L equals 1, that corresponds to a p orbital. So that would be the 2p subshell. Okay? And what this tells you is how many actual orbitals are there in that subshell. It could be 1, it could be 3, it could be 5. We're going to see that it's always an odd number. But yes, this m sub L tells you how many there are. So how do we get that? We get it from the rule. Now, this is the most confusing rule, but it's actually really, really easy. Again, you just have to let go of this as telling you, as trying to tell you a rule for what m sub L is. And remember, this is a rule for telling you what m sub L could be. And what it basically says is once you already know your L value, then you take minus the L value and you start adding 1 to it till you get back up to the L value. Okay, so in other words, for here, L equals 1. What could we do for m sub L? So m sub L, we would take minus the L value, that's minus 1, and then we start adding 1 to it. Minus 1 plus 1 is 0, and then 0 plus 1 is plus 1, and we've reached L again. So m sub L here could be minus 1, 0, or plus 1. So let's do another example. What if L equals 3? What are the possible allowed values of m sub L? So m sub L is allowed to be minus L. So what is minus L? Minus L is minus 3. And then we're just going to start adding numbers to it. So -3, -2, that's minus L plus 1. And then we would have -1, that's minus L plus 2, and so forth and so on. So then the next one we would have would be 0, and then we would have plus 1, then we would have plus 2, and plus 3. So these are the total number of possible IMSA-bells. Now, all you have to do then is count these numbers, and that will tell you how many orbitals there are in that subshell. So there's 1, 2, 3, 4, 5, 6, 7. So there are 7 orbitals in this subshell, and you'll see exactly how all this works in a minute. So if you're confused right now, don't worry about it. We're going to go through. We're going to work a bunch of examples, and you'll see how all this works very shortly. So here's a question: how many degenerate orbitals exist in a subshell with L equals 2? So if we have L equals to 2, then the allowed values of IMSA-bell are -2, -1, 0, +1, and +2. Okay, so then we just count this, and the total number here is 5. So the answer is 5 degenerate orbitals. Remember what degenerate means. Degenerate means that the orbitals just have equal energy. So if we draw a diagram where we're looking at energy on the y-axis, we would put all of these orbitals on the same energy level. We typically draw orbitals as just dashes. So all of these would have the same energy. We could call this one -2, this one -1, this one 0, this one +1, and this one +2. And those would be degenerate orbitals. And other subshells would have different energies. We might have something like this, where we have 3 here, and then 5 here, and then 1 here, and so forth and so on. So different energies for the different subshells, but within a subshell, they have the same or equal energy. They're degenerate, and how many you find here, you count the numbers of IMSA-bell values to determine how many total orbitals you have in a region like this. Okay, so let's just kind of go through and look at the standard examples. What if we have L equals 0? Well, then the only value of IMSA-bell is 0. That's the only one we can have, which means L orbitals, which are s orbitals, so these s orbitals with L equal to 0, occur in sets of 1. So that means that we can have a 1s orbital, we can have a 2s orbital, we can have a 3s orbital, we can have a 4s orbital, but we only get 1 s orbital per quantum number, per principal quantum level. So that's an n value. And notice n value goes up 1, 2, 3, 4. So again, we're going this kind of smaller to bigger as we go up. This would be the 1s, this would be the 2s, this would be the 3s, this would be the 4s. But on each floor or on each level, you only get 1 s orbital. Okay? All right, well, then what about p orbitals? So let's look at p orbitals. And you'll notice p orbitals occur in sets of 3. So if we have L equals to 1, then what are our allowed values of IMSA-bell? IMSA-bell would be equal to possibly -1, 0, or +1. And that's 3 options. So we name these things PZ, PX, and PY. We name them PZ, PX, and PY, but we could also label them as -1, 0, and +1. That's a way that we could potentially label these orbitals, because one of them would have IMSA-bell -1, one of them would have IMSA-bell 0, and the other one would have IMSA-bell +1. So let's say we were talking about the second floor. So that would be n equals 2. That's the second floor, the second shell around the outside of the atom. And then we would have L equals to 1, and then we have the 3 possible IMSA-bells. That would be +1, 0, and -1. I don't know why I wrote them in the reverse order. It doesn't matter what order you write them in, but there's the 3 possibilities. So if this is our -1, our 0, and our +1, then what would the psi be for this one? The psi would be 2, 1, -1. So that's the official designation of the wave function that this orbital represents. Which one would this one be? This one would be psi 2, 1, 0. And this would be psi 2, 1, 1. So my minus 1 looks terrible over here. I'm gonna redraw it. 2, 1, minus 1. Okay, so each orbital has its own unique set of 3 quantum numbers labeling it, and it has its own shape and its own size. Okay, so the n value tells you how big it is, the L value tells you what shape it is, and this m sub L value tells you which direction it's pointing. Okay, and that's the basic way that these problems work. Let's look at the d orbitals just to finish this up. So what are the possible values of d? So for d orbitals, L equals 2, which means we have m sub L, the 5 possibilities are minus 2, minus 1, 0, plus 1, and plus 2. And again, it doesn't matter which ones we call which, but we could call this one minus 1, we could call this one 0, we could call this one plus 1, this one minus 2, and this one plus 2. So we have 5 different possibilities. Now notice for the d orbitals, 4 of those possibilities are going to be the cloverleaf shape, and one of them is going to be this sort of p orbital with a donut around its shape. So 4 of them look like cloverleafs. One of them have this donut with a torus around it. Or excuse me, this p orbital with a torus around it. So those are the 5 different d orbitals. You can see pictures, look up online if you want to see pictures of L equals 3. Those are f orbitals, and you'll see they're much more complicated, but you don't need to memorize them. So these are the only shapes that I expect you to know. But if we were to do f orbitals, and again, we're not going to look at them, but if we were to do f orbitals, how many of them would there be in each subshell? So an f orbital is L equals to 3. So we would have m sub L is equal to minus 3, minus 2, minus 1, 0, 1, 2, and 3. And that's 1, 2, 3, 4, 5, 6, 7. So so f orbitals occur in sets of 7, and you would have 7 different pictures for the 7 different orbitals that are f orbitals. Okay, so let's make a table then of atomic orbitals. So here's what we're going to do. We're going to list our quantum numbers. So I have n here, I have L here. Well, let's give ourselves a little bit of room. Let's put L here, and we have m sub L here. So for n equals 1, all right, and here's, by the way, let me give you the little cheat. The little cheat is that n has to be greater than L, which has to be greater than or equal to the absolute value of m sub L. So that this little rule here tells you if your numbers are correct or not. So in other words, if I give you a psi and I say that psi is 2, 2, 1, is that an actual solution to the Schrodinger equation for the atom? Well, you look at n, you look at L, and you look at m sub L, and you follow this rule. N has to be greater than L has to be greater than or equal to the absolute value of m sub L. Well, 2 is greater than 1, so L is greater than m sub L, so that part's fine. But here we have 2 is equal to 2, not greater than. So this is not a possible solution. So that's not a real orbital. There's no real orbital there. On the other hand, I could have something like this, 3, 0, 0. And n3 is bigger than L, 0 is bigger than or equal to m sub L, 0. And so this one's fine. That one is an orbital or a wave function, and you can graph it as an orbital by squaring it and checking the probability distribution through in the space around the atom. So let's figure out which combinations we can actually put in. Which combinations can we put in here? So let's start with n equals 1. So the only allowed value of L then is 0, right? It has to be 0 up to n minus 1, but n minus 1 is 0. So that's 0. So that means the only thing we have on the first floor is an s orbital. And for m sub L, the only thing we have is also an s orbital, and that would be the 0 one. So I'm just drawing the picture of it here. So and so here we would have is the 1s. That's it. What about n equals 2? Well, n equals 2, we would have 2 possibilities. L could be 0, And if L is 0, M sub L could only be 0. So there's only one possibility here, but this is also an s orbital. So here we would have a 2s orbital. But L could also be 1, and that will correspond to p orbitals. So on the second floor, we're going to think of the atomic structure as being sort of like a skyscraper. On the first floor, you only have one apartment, and that apartment is an s orbital, and it has m sub L equal to 0, and that's it. One s, that's all you have. On the second floor, you have two sets of apartments. You've got an S suite, and there's only one apartment there, and that's the 2S. And you have a P suite, but P orbitals occur in sets of 3. So we call those the 2P orbitals. And those are the 2P X. And again, you don't have to know this, but the 2P Y and the 2P Z. And I'm not going to write these down for each of the following ones, but those are the orbitals, and that's everything that you can do on the second floor. Okay, so we've maxed out the second floor. Now we go to the third floor. The third floor, again, we have 0. That's a possibility. That's an s orbital. Again, we have 0 as the possibility for m sub L, and the only thing we have here would be a 3s. So here would be a subshell that contains one orbital, and it's an s-type orbital. But then we would have another subshell that would have p orbitals, and that would have -1, 0, and +1. And that would be our set of 3p orbitals. And then we also now have the possibility of 2, because 3 minus 1 is 2, so L can be 2. So that means there are also d orbitals on this floor, which means we also have -2, -1, 0, +1, and +2. So that would be 1, 2, 3, 4, 5. Okay, so there's our orbitals for the d orbitals as well. And then you would go up to 4, and for 4, I'm not going to do them all. You would have 0, you would have 1, you would have 2, and you would have 3. 0 would be the s orbital, so there would be a 4s orbital. 1 would be the p orbitals, so there would be a set of 4p orbitals. 2 would be the d orbitals, so there would be a set of 5 4d orbitals. And 3 would correspond to the f orbitals, which would be a set of 7 4f orbitals. There would be 7 4f orbitals. And each time you go up a layer, you add another L, and you add a bunch more orbitals. So each time you go up, you get many, many more possible orbitals. So it's kind of like an upside down skyscraper. The first floor only has one apartment. The second floor actually has 4. It's got one S, and then it's got 3 Ps. The third floor actually has 9. Notice it's got one S, it's got 3 Ps, so that's 4, and then it has 5 Ds. These are the 3D orbitals, and there are 5 of them. So that's actually 9. So you'll notice the total number of orbitals, the total number per quote floor is n squared. So if we take 1 squared is just 1, and we only end up with one apartment, one orbital. If we look at n2, 2 squared equals 4, and there are 4 orbitals that we could work with here. N equals 3, 3 squared equals 9. 3 times 3 is 9, and here we have our 3s, our 3 3ps, and our 5 3ds. 5, 3, and 1, that's a total of 9. And when you get down to 4, then 4 squared would be what? 4 squared, 4 times 4 is 16. So we have 16. So when you add in the f orbitals here, we would have 1s, 3ps, 5ds, and 7fs, and if you add those together, you'll get 16. So a quick way to tell how many apartments or how many orbitals do I have on each floor is just take the floor and square it, and that will tell you the total number on that. So this is a table of atomic orbitals, and you can continue this down as far as you want to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as far as you want to go, and those are all the different possible solutions to the Schrödinger equation for the hydrogen atom, and indeed for other atoms as well. Okay, so what I want to do is move on a little bit. So we have three quantum numbers associated with the solution to the Schrödinger equation for the hydrogen atom. We also have a fourth quantum number, but the fourth quantum number doesn't have anything to do with the hydrogen atom. The fourth quantum number is something that the electron has on its own. So even an electron that's not in an atom, that's just flying around in space, say electron moving through a conductor, so an electron is part of an electric current, or just an electron flying around through empty space, also has its own quantum number. And this quantum number is called its spin. And basically what happened is the electron will, it behaves like a little magnet. So you can imagine the electron as being a little magnet. It's got a north pole and a south pole. And the electron will then line up either with the south pole pointed up or with the north pole pointed up. And so we say that if the south pole is pointed up, we call that a spin up. So this picture here, we would call this picture spin up. If the north pole is pointed up, we call that spin down. That's just terminology. And for spin up, we give it a quantum number, and we call that plus 1/2. And for spin down, we give it a quantum number, and we call that minus 1/2. So the only allowed values for this, and there's a typo here, so I'm going to fix it. That's this m sub l. So what we should have is m sub s. So hopefully this works. There we go. M sub s is allowed to be equal to plus or minus 1/2. And if it's plus 1/2, that means we've got the little magnet oriented this direction. If it's minus 1/2, we've got the little magnet oriented in the other direction. And you say, wait a second, can the magnet point any direction it wants to? Can it point over to the left? Can it point over to the right? The answer is actually no. This is one of those weird things with quantum mechanics. Every time you measure, if you take an electron and you try to measure it, you will always find it pointed up or down. You'll never find it pointed off to a direction that's not up or down. Why is that? Because the only way to really measure this is to put it in a magnetic field. And once you put it in a magnetic field, it's either going to align with the magnetic field or against the magnetic field. It can't align sort of sideways. Real magnets, like a magnet, if you take a magnet off your refrigerator door, you can force those to not line up. You can take one and you can stick it south to south or north to north. You'll feel the energy, the repulsion there, but you can do it. You can also take two bar magnets and put them crossways across each other. You can have one south and north this way and then one south and north this way. No problem with that, or any other angle you want to. But it turns out in quantum mechanics, for an electron, you can't do that. They either line up spin with a magnetic field or they line down spin with a magnetic field, and they can't line up any other direction. So it's always going to be plus or minus 1/2. All right, so that's called the spin of an electron. It's an important quantum number. And again, that one's just something the electron has by itself. So if we want to talk about the state of an electron in an atom, we have to say what orbital is the electron in, and we also have to say what is its spin. Is it spin up or is it spin down? So for an atom, an electron is going to have 4 quantum numbers. It's going to have an n, an l, an m sub l, and it's going to have an m sub s. So let's do an example. What are all the possible sets of 4 quantum numbers for an electron in an atom when n equals 2? All right, so here's what we can do. We're gonna make a little table. So here's our n. We know that n equals 2. What are the allowed values of L? The allowed values of L here are 0 and 1. Those are the only possibilities. What are the allowed values of m sub L? For this first one, this is an s orbital. And so the only allowed value here is just 0. For this one, we have a p orbital. So we have 3 possibilities. We have the possibility -1, we have the possibility 0, and we have the possibility +1. And then we also have an m sub s to deal with. So for 2, 0, 0, we could either be plus 1/2 or we could be minus 1/2. For 2, 1, minus 1, we could be plus 1/2, or we could be minus 1/2. For 2, 1, 0, we could be plus 1/2, or we could be minus 1/2. And for 2, 1, 1, we could be plus 1/2, or we could be minus 1/2. So let's count all the total number of possibilities. That's one possibility here. That's two possibilities here. 3 and 4 possibilities here. 5 and 6 possibilities here. 7 and 8 possibilities here. So there are 8 sets of unique quantum numbers for an electron with n equals to 2. So if you tell me I only care about electrons that are in the second floor, the second shell, then I will tell you, well, there are 8 possibilities. And notice the number of possibilities is n squared times 2, because n squared is the number of apartments. And what this is essentially telling you is you could put in an electron that's plus 1/2, or you can put in an electron that's minus 1/2, and those are the ones that could go into that apartment. So that means twice for each apartment. There's 2 electrons, so you can do 2n times 2. So that would be 2 times 2 squared, which is just 8. So you can actually do this a lot faster by knowing this, but I don't want you to just use this. I want you to be able to draw out these pictures and look at all the different possibilities. 2, 0, 0 plus 1/2, 2, 0, 0 minus 1/2, 2, 1, 0, 2, 1 minus 1 plus 1/2, 2, 1 minus 1 minus 1/2, 2, 1, 0 plus 1/2, 2, 1, 0 minus 1/2, and finally 2, 1 plus 1 plus 1/2, and 2, 1 plus 1 minus 1/2. Those are all 8 possible combinations of quantum numbers we can have for electrons with n equals to 2. Notice as n gets bigger, this number is going to go up like crazy. So for n equals 3, 3 squared is 9, 9 times 2, there's 18 possible ones. And then when you get to 4, 4 squared is 16, 16 times 2 is 32. There's 32 possible combinations for n equals 4. So as we go up, this gets more and more complicated. Okay, so let's look at the orbital energy diagram for hydrogen. Let's just build it up. So when we say orbital energy diagram, what we do is we graph the energy over here versus we just stack the orbitals on top of each other. So we're going to start down here with n equals 1. Remember, for the hydrogen atom, you only need to know n to know the orbital. So what we have is we have a 1s orbital. That would correspond to n equals to 1, L equals to 0, and M sub L equals to 0. So that's our first floor. And then we go up to n equals 2, and we have a 2s orbital, but we also have a set of 2p orbitals. So this would be n equals 2, L equals 0, and M sub L, of course, is 0. Then here we would have n equals 2, L equals 1, and we would have minus 1, 0, and plus 1 as the combinations here for these 3 orbitals. Then we go up to n equals 3, and we would have a 3s, a set of 3p's, and a set of 3d's. And then we would go to n equals 4, and we would have a 4s, a set of 3p's. Remember, p's occur in sets of 3. That would be that should be 4p. And then the d orbitals occur in sets of 5. 1, 2, 3, 4, 5. Those are the 4ds. And 4 also has the possibility of f. So that occurs in sets of 7. 1, 2, 3, 4, 5, 6, 7. And that would be the 4f's. And then we could keep going. We could do n equals 5 and as high as we want to go. And notice each time you go up a floor, you add a new level. And that's because you can add an extra L. Here, L can only be 0. Here, L can be 0 or plus 1. Here, L can be 0, plus 1, or plus 2. Here, it can be 0, plus 1, plus 2, or plus 3. And as you go up, it can be one unit higher each time you go up. So this is the picture for hydrogen. Notice that this explains the Bohr model. The reason being, if we put an electron in, let's say we typically show an electron with an arrow, and we'll talk more about this in just a minute. But if we put an electron in and say that's n equals 1, this would be the ground state. And then we can take and move this up to an excited state, any one that we want to. So this would be an excited state. But notice it doesn't matter which one of these I put the electron in on the 4th floor. They're all the same energy. And so as far as we're concerned, to know the energy, which is what the Bohr model told us, to know the energy or the difference in energy between levels, all we need to know is n. We don't need to know which of these other orbitals it's in. So the Bohr model only needs n in order to tell us what happens for hydrogen. But what we'll see is that for all other atoms, these orbitals' energies change and they get mixed up. And for those, you need both N and L to tell you the energy. And that's why the Bohr model failed, because the Bohr model only used one quantum number, and the true solutions, or the better model, I should say, the better model, the quantum model, requires 3 quantum numbers to distinguish which orbital that we happen to be in. So let's just, as one last time, say how we would get the psi. So let's say that I'm looking for this one, and I want to know what the subscripts are for psi for that orbital. So which wave function gives this orbital? So the first one, the first letter here is from the the first number is from n. So the first number there would be 4. That's our first subscript. The second one would come from the value of L. And so L in this column is 0, L in this column is +1, L in this column is +2, and L in this column is +3. So that would be 4, 3. And then in truth, it doesn't matter which order you number these for M sub L. There's no difference in energy. So you could call this one -3 and this one over here +3, or vice versa. But traditionally, we are just going to number them, traditionally we number them from left to right: -3, -2, -1, 0, +1, +2, and +3. So we would actually just have this as 4, 3, and -1. And that would be the wave function corresponding to that orbital. And you can do this for any one of these. Every single dash, every single orbital that I've drawn on here has its own unique wave function. How do we show the electron spin? If we draw an arrow up like this, that is m sub s equals +1/2. And if we were to come in and draw an arrow down like this, we would say that would be m sub s equals -1/2. So if I drew a picture like this and I put an electron here and asked you to tell me what are the 4 quantum numbers for that electron, what you would do is you would say, okay, what is the n level? That's 4, so n equals 4. What is the L? That's +1, +2, +3. That's the 0, 1, 2. That's L equals 2. M sub L is kind of arbitrary, but we're going to choose it to be -2, -1, 0, +1, and +2. So here we could call this +1. And then M sub S is our spin, and notice my arrow is pointed down, so that would be -1/2. So this is the set of 4 quantum numbers that is the location for this particular electron. And again, you can draw any electron in any one of these pictures, in any one of these places, and you can find a set of 4 quantum numbers that would tell you that that's where that one happens to be. Okay, so let's move on then.